Hello everyone, and welcome back to our physics session. Today, we're diving into one of the most fascinating objects in the universe, black holes. Specifically, we'll calculate the radius of the event horizon for a non-rotating, non-charged, or Schwarzschild black hole. This boundary is crucial because it represents the point of no return. Once anything, even light, crosses it, escape is impossible. Understanding this helps us grasp the extreme nature of gravity and the structure of spacetime itself. Let's break this down step by step. First, imagine our black hole. We can't see it, but we can visualize its key features. At its very center is a singularity, an infinitely dense point. Around this singularity, we draw a perfect sphere. This sphere represents the event horizon. Its radius, from the center to this spherical boundary, is what we aim to calculate. Now, let's identify our key variables and constants. We're given the mass of the black hole, m, as 5 times 10 to the power of 30 kilograms, 5 times 10 to the 30 kilograms. This is the enormous concentration of mass that creates such immense gravity. We'll need the universal gravitational constant, g, which is approximately 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared, 6.674 times 10 to the negative 11 Newton meters squared per kilograms. This fundamental constant quantifies the strength of gravity. And finally, the speed of light in a vacuum, c, which is approximately 3.00 times 10 to the 8 meters per second, 3.00 times 10 to the 8 meters per second. This is the ultimate speed limit in our universe. Our unknown, the quantity we're solving for, is the Schwarzschild radius, Rs, which is the radius of the event horizon. The fundamental principle we apply here comes from Einstein's theory of general relativity. For a Schwarzschild black hole, the event horizon is defined as the radius at which the escape velocity equals the speed of light. This leads us directly to the Schwarzschild radius formula. Rs equals 2gm over c squared. This equation directly links the mass of the black hole to the size of its event horizon using these universal constants. Now, let's substitute our known values into the equation. Rs equals 2 times 6.674 times 10 to the negative 11 Newton meters squared per kilograms times 5 times 10 to the 30 kilograms over 3.00 times 10 to the 8 meters per second. Performing the multiplication in the numerator, 2 times 6.674 times 5 gives us 66.74. And for the powers of 10, 10 to the negative 11 gives 10 to the 19. So the numerator is 66.74 times 10 to the 19. For the denominator, 3.00 times 10 to the 8 squared gives us 9.00 times 10 to the 16. Now, divide the numerator by the denominator, 66.74 times 10 to the 19, over 9.00 times 10 to the 16. 66.74 times 9 is approximately 7.4155, and 10 to the 19 over 10 to the 16 is 10 to the 19 minus 16, or 10 to the third. So Rs is approximately 7.4155 times 10 to the third meters. This works out to approximately 7,416 meters, or about 7.42 kilometers. To check our answer, we can quickly verify the units. If you carefully combine the units of g, m, and c squared, you'll find they simplify directly to meters, which is what we expect for a radius. Furthermore, a black hole of this mass, roughly 2.5 times the mass of our Sun, is expected to have an event horizon a few kilometers across. So, our result is physically reasonable. In conclusion, for a non-rotating, non-charged black hole with a mass of 5 times 10 to the power of 30 kilograms, its event horizon, the point of no return, is approximately 7.42 kilometers from its center. This calculation highlights how the immense gravitational pull of a compact mass warps spacetime, creating a boundary from which nothing can escape. This concept is fundamental to understanding stellar remnants and the massive black holes at the centers of galaxies. This formula, Rs equals 2gm over c squared isn't just for this specific mass, it's a universal relationship. You can use it to calculate the Schwarzschild radius for any mass, whether it's a star, a planet, or even yourself, if that object were hypothetically compressed enough to become a black hole. It provides a foundational understanding of what defines the size of a black hole and how it scales with mass. Thank you for joining me for this deep dive into black holes. If you found this explanation helpful, please consider liking this video, subscribing to our channel for more physics breakdowns, and sharing it with anyone who loves science. Your questions and comments are always welcome below. And remember, if you have a specific physics problem you'd like to see solved, consider donating to the channel. Each month, we'll select a few problems submitted this way and dedicate a full video to them. See you next time.